So, I should mention just before I get started with the material part, the lab quiz results should have been made or given to you on Friday night. So it looks like the way that it works is you'll start writing on the Mondays, or the lab session will open on the Mondays and be due on the Tuesdays at 8 p.m. The grades are then, or the quizzes are then graded, and the full grade is returned to you on Friday. And the reason for the 3-day sort of lag between results and feedback is due to there being students that have to have accommodations made in terms of time allowed and when they write, also to correct any mistakes that might have been made in the grading itself. And so we give ourselves about a 72-hour period there just to sort out all the marks. So on Friday, you should be presented or given your grades on the quiz, and there should be feedback that is somewhat undetailed, I admit, but it tells you which questions you got wrong. So at that point, if you have a particular interest in looking at or understanding what went wrong on a particular question, you can email me and say, I don't understand what happened here, or I don't understand why I lost a mark on question 2, for example. And I can give you an example of the question that we were working with and an example of the solution that we were expected to have, or you were expected to give. So in some cases, the issue might have been a rounding issue. In some cases, it might have been including a sign that you weren't supposed to include, these sort of things. I think the marking software is very sensitive to details like that. So you can let me know which questions you're curious about, and I can tell you the feedback. The reason that you do not get shown the exact question is because there is a very small pool of questions that we can draw from for the quizzes. So we are trying to keep the questions kind of in-house for editing and to be used as tools in the future. So that's why the questions are not returned directly to you. But again, if you have a particular question about a particular, or if you have an inquiry about a particular question on the quiz, you can email me about that question, and then I can provide you with sort of an example of what that question was asking, not word for word, of course, and I can explain to you what the solution would have been based off of that question. And hopefully that will give you feedback that will help you on the future quizzes and on the lab final, though I don't think that one's run through Blackboard. Okay, so that's the first part. Oh, nice. Okay. Okay, so that's the first part. Now the second part of today's lab. Okay, so first off, let me just write down here so that we're on the same page. The topic here is binomial probability calculation using Rcmdr. Okay, so this is what we're going to learn today. Now, before we get there, okay, we have to discuss the binomial probability distribution. Okay, so some of you may have seen the binomial probability distribution already. You will be taught about this distribution sort of in its entirety in lecture. So for example, if you're in my 9:30 a.m. lectures on Tuesday and Thursdays, I discussed this distribution this morning in my first lecture. If you're in my 2 o'clock lecture, I haven't gotten to it yet. So there's some of you that might have seen this already, at least the formula, and had an explanation of what it is, hopefully that was satisfactory. And some of you may not have heard of this at all, which is fine. I'm gonna go over it now. Some of you might just be getting to it. The assumption is that we're all sort of in a different place at this point. So in order to accommodate using Rcmdr, working through the examples, and giving you guys time to work through some of the problems at the on assignment 4. Note that there's only one lab question on assignment 4, and it is just asking you to verify using Rcmdr some of the calculations you will do by hand in question 4 on that assignment. So there's no data set required on assignment 4. It's a simple verification of what you do by hand. So it's a very short lab portion this week. So in order to accommodate all of these things, so explanation, illustration, and work time after, I'm going to give sort of a brief overview of what the binomial probability distribution is and what it does. And then gaps that I leave will be filled in lecture. Okay, so hopefully this will be enough to kind of get you going. And then anything else that you need, hopefully you'll get through your lecture. Okay, first, the binomial probability distribution. What is the binomial probability distribution? Okay, one. It is a discrete random variable distribution. Okay. 2, what is the discrete random variable distribution? Okay, a discrete random variable distribution through illustration, okay, is a distribution where some random variable that we call x can take on some number of values. Okay, so for example, 0, 1, 2, and 0, 1, and 2. And associated with those is some probability. So let's say 0 0.2, 0 0.6, 0 0.2, just for illustration. Okay, so explanation here. It's a distribution that provides the probability of observing some outcome where the outcome is a value of the variable of interest. Okay, so what I'm trying to say here is that suppose you have some value that is of interest to you. So in this very simple illustration, the values of interest to us are 0, 1, or 2. Okay, but we can extend this to many, many different situations. Associated with each of those values is a probability. Okay, so the only requirement is that those probabilities have to add to 1. Okay, so 0 0.2, 0 0.6, 0 0.2, for example. You add those three together, you get 1. We call capital X here. Okay, so this is our discrete random variable. We call capital X a random variable because there's a probability associated with its outcome. So the probability that I observe a 1, for example, is 0 0.6. So you can think of an experiment that consists of, let's say, picking a number out of a hat, or picking a piece of paper out of a hat. Let's say that we have an infinite pieces of paper inside of this hat. Written on each piece of paper is a number, 0, 1, or 2. I pull out one number. The probability of that is a 0 is 20%. I pull out the next number. The probability it's a 1 is 60%. I pull out the next number. The probability it's a 2 is 20%. Okay, so there's this randomness or probability associated with each of the different outcomes. When the outcome is a whole number, we call it discrete. Same definition that we had back in week 1 of the course. All right. So then we have how to build a binomial. So the idea here, based off of question 1 and 2, is a binomial distribution is obviously some special case of a discrete random variable distribution. So the discrete random variable distribution is kind of this overlapping definition for any random variable that takes on a whole number value, and associated with that whole number value is a probability. The binomial is a special case of that. So the binomial distribution admits the same type of illustration that we saw above. So we could sketch a discrete random distribution table like I have in question 2 for question 3. But more formally, the binomial models successes across little n Bernoulli trials. Okay, so the binomial distribution is used to count the number of successes that we would observe across n Bernoulli trials. All right, well then the question is, of course, what is a Bernoulli trial? I'm going to flip over to a new piece of paper here. So the Bernoulli trial is a trial, or is an experiment, is a single experiment where two complementary events, or sorry, where one of two creates the outcome. Okay, so the Bernoulli trial refers to an experiment where one of two things can happen, this or its opposite, in all situations. Okay, so example, coin flip. Two outcomes, head or tail. Okay, and the probability of head plus the probability of tail equals 1. Okay, win or loss, right? So we have two outcomes, assuming no ties, win or loss. The probability of win plus the probability of loss equals 1. So the Bernoulli trial refers to any illustration where, or any single experiment where you can only have two outcomes, this or the opposite. So we can think of that as success or failure. So in general, success or failure. Okay, and then you have P of success plus P of failure equals 1. Okay, that's the overarching idea. Two outcomes, they are complementary outcomes. And when we do this one time, we call it the Bernoulli. So the binomial is a sequence of n of these being put together. So the binomial experiment is one where we perform the exact, or we perform the same Bernoulli trial over and over and over again, and then we are interested in computing all of the successes that we could observe that are possible across those n trials. Okay, so here we go. For example, okay, so flip a coin, little n equals 5 times. Okay, so what's happening here is we have 1, 2, 3, 4, and 5. Okay, and we have head, or we have tail, 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 we have head, or we have tail. Okay, and these are the outcomes. All right, so each individual trial here is a Bernoulli. Okay, so each of these is a Bernoulli. All right, now the binomial has the following outcomes, okay? So the binomial is going to count successes, let's say heads, across the n equals 5 trials. Okay, so the binomial is going to look like this. We'll have capital X is 0, 1, 2, 3, 4, 5. Okay. So again, our Bernoulli experiment refers to the individual experiment where something is happening one time, a coin flip, most basic illustration. The outcomes of that coin flip, of that Bernoulli trial, are complementary. So you either have this thing or its opposite. The probabilities have to sum to 1. That's a requirement of the Bernoulli. If we perform n Bernoulli trials, so let's say we flip a coin 5 times. By doing that, what we can now do is actually count how many times we observe a success across the n trials. So let's say I flip a coin 5 times. I want to know across those 5 times what is the probability that I get 0 heads? Or what is the probability that I get 2 heads, 3 heads, 4 heads, 5 heads, or 1 head, for example. Okay, those would be the different number of successes across those 5 trials. Those successes, the counts of those successes, become what is called binomial. Now, for the individual Bernoulli trial, it's very easy to construct a distribution. Okay, so for each Bernoulli trial, we have a head or we have a tail, and then we have the probability associated with it. Okay. For the binomial, you can see the table is quite a bit more complicated. We have 0 heads, 1 head, 2 head, 3 head, 4 head, or 5 heads. We want to know the probabilities of these different outcomes. Okay, so we want to know the probability I get no heads across 5 trials, or I get 1 head across 5 trials, or I get 2 heads across 5 trials, 3 heads, 4 heads, or 5 heads, for example. How do we do that? All right, well, the binomial probability formula tells us that the probability that little x is equal to x is equal to n choose x. Note that this here is the same thing as n cx times p to the x times 1 minus p to the n minus x. Right? So for each of those outcomes, we can use this formula to find the probability of those of 0, 1, 2, 3, 4, or 5 in the illustration. Okay, so for example, the probability that x is equal to 0 is equal to 5 choose 0, 0.5 to the 0, 1 minus 0.5 to the 5 minus 0, for example. Okay. So that's going to give us 5 choose 0 times 1 times 0.5 to the 5. Okay. And that is 0.0312. And then we can do the same thing for the other values in the table. So if I want the probability x is equal to 1, I would have 5 choose 1, 0.5 to the 1, 1 minus 0.5 to the 5 minus 1. That gives me 5 choose 1 times 0.5 times 0.5 to the 4. And that gives me 0.15625. Okay, and then I can continue on in this pattern to compute each of the values in the table. All right, so what we're going to be learning how to do in Rcmdr is this calculation. Okay, so we are going to learn this calculation in Rcmdr. Okay, so that's the goal for today. Any questions? Okie dokie. So let's turn this off. Okay, so can you guys see the Word document here? And then if I do that, can you see R? Okay, so in Rcmdr specifically, all right, if we want to perform a binomial probability calculation, we click, all right, here, let me make this a bit bigger for everybody. Okay, we click distributions, discrete distributions, binomial distribution, and then we have two options, binomial probabilities, binomial tail probabilities. All right. So if we click binomial probabilities, and then we choose our sample size, which is 10, and we click OK. This is a very helpful table because it actually gives us, for example, all of the probabilities associated with each event. So let's do, for example, maybe a better illustration. Okay, so 5 here. So in the illustration that I was using at the start of class with the coin flips, we flipped the coin 5 times, okay? So we do 5 coin flips. The probability of success on each coin flip is 0.5. If I do that 5 times, this table gives me the probabilities of each different outcome. So this is saying the probability that I get 0 out of 5 successes, so let's say 0 out of 5 heads, is 0.03125. The probability that I get 1 out of 5 heads is 0.15625. The probability I get 2 out of 5 heads is 0.3125. The probability I get 3 out of 5 is 0.3125. 4, 0.15625, and 5, 0.03125. So this table is giving me the probability of each individual event, but it's listing it across the entire sample size. So if our sample size, if the number of trials gets really, really big, this table is going to be really, really long, which will make it a bit harder to dissect. How do I get that on there? So the table that I produced here is found by clicking distributions, discrete distributions, binomial distribution, binomial probabilities. So that's the first example that I worked through. So if I click this, I select my probability of success on each trial. So for a coin flip, it would be 0.5, for example. And if I perform 5 coin flips, that's the number of trials that I'm going to have here. And then I just click OK. Did you get that, Taylor? Okay, sweet. Okay, now the other calculation we have is binomial tail probabilities. Okay, so what is the binomial tail probability showing us? When we have lower tail selected, this is giving us x is less than or equal to some value. Okay, so for example, let's say that we have 5 trials, and let's say that the probability of success is 0.5 again. So we're doing 5 coin flips. Now let's say that I have lower tail selected, and I do 3 as my variable value. What I am asking here is, what is the probability that I am less than or equal to 3 heads? So what is the probability I observe 3 or less heads? So if I click OK, I get 0.8125. The 0.8125 is the sum of the probability at 0 plus the probability at 1 plus the probability at 2 plus the probability at 3. Okay. So the command here is giving us the probability that x is less than or equal to some value in our set number of trials. So if I do 5 coin flips and I want to know the probability that x is less than or equal to 3, then I would do distributions, discrete, binomial tail. I set 3 as my variable value, 5 trials, the probability of success on each trial, and I select lower tail. And that will give me less than or equal to 3, which is the same thing as x equals 0 plus x equals 1 plus x equals 2 plus x equals 3. And you can see from the table that we printed out using the first command that adding 0, 1, 2, and 3 together gives us this value. Now if I select upper tail, what is this going to give us? Okay, 0.8175. So the upper tail command is telling us the probability that x is strictly greater than 3, which is x being greater than or equal to 4. Okay. And then you can verify that by adding the probabilities from the table. So we have distributions, discrete, binomial probabilities. Binomial probabilities give us our table where we give probability of success on each trial and we give the number of trials. The binomial tail probabilities give us the probability that x is less than or equal to some value, that's the lower tail, and the probability that x is strictly greater than that value, which is the upper tail. So we have effectively 3 different computations that we can use. All of them are using the formula that I illustrated earlier as the underlying calculator, if you will, or the formula that helps us find these probabilities. And we can utilize Rcmdr to exploit these different relationships to find probabilities that are of interest to us. Okay, so let's look at some examples of that. All right, so in the demo file that's on the lab merged website, we have 2 questions that are binomial questions, question 8 and then question 9. So in question 8, we have data collected from Wikipedia. This data in 2016, let's suppose that it's comprised of n is equal to 1,000. So we're assuming that capital N is equal to 1,000 here. We want to find the probabilities below, assuming that we can view the percentages in the 2016 column as probabilities of success. So we're making quite a few different assumptions here that probably aren't realistic, but for the purpose of illustration, we're going to assume that each person, each of these 1,000 people are independent of each other, and that the probability of them belonging to a particular minority is the same, such that we can treat them as being part of a binomial experiment. If possible, could you show us an example of determining the probability distribution of a random variable x today? Yeah, like, sorry, what do you have in mind exactly? Like just the general random variable, or? Sure. Okay. All right. So, okay. Well, I'll try and answer your question first, and then I'll come back to this. And I'm going to make an assumption that I can. So let's say to find the probability distribution of a random variable. Okay. So let's import some data from Excel. Okay. So I'm just going to use the traditional lab data set here. So QN lecture. I meant using the formula. Like the binomial probability formula. Okay. So okay, maybe better put, the values that are shown here that I have highlighted, are you asking how to find each of these values specifically? Okay. So I did do this already. I can show you that. Okay, hold on a second. So I can make this work. Uno momento. Only one moment. Only one moment. Ah, okay. I see what's going on now. Okay. All right. Okay, so in this illustration, if we wanted to make a the probability distribution of x, so we're going to have the following here. So X can take on 3 different values, 5, 7, and 8. Okay. So we want to find the probabilities of each. To do this, we're going to sum the frequencies together. Okay, so that's going to give us 125. And then each probability is going to be the frequency divided by the total. So P of X is equal to 5 is going to be 25 divided by 125, for example. Okay, and then we're just going to repeat that calculation for each of the different values. Yeah, they do. So the binomial distribution is a special case of the discrete random variable distribution. So if we wanted to determine the discrete random variable distribution using a frequency table, we would sum the frequencies and then just divide that total by each of the frequencies for the column. Does that make sense? Okay, sweet. Okay, sorry. So illustrations of the binomial probability formula using Rcmdr. So we're going to assume in this illustration, we're focusing on the percentage column for 2016. So that's the last column shown here. Okay. We are going to assume that little n is equal to 1,000. Okay, so that's going to be our number of trials. And basically what we're interested in doing here is determining the probability that we observe a person of a certain ethnicity using these probabilities of success. So for example, what is the probability that I observe between 30 and 39 persons that identify as Black? So what I'm asking here, I'm just gonna clean this up a little bit. Okay, so what I'm asking more straightforward is, what is probability that I observe between 30 and 39 persons that identify as Black? Okay, so what we're saying here in this case is little x is equal to 30, 31, 32, 33, 34, 35, 36, 37, 38, and 39. Little n is equal to 1,000. And p, which would be equal to the probability observing a person who identifies as Black, is going to be equal to 0.035. Okay, so this 3.5% here in the final column in the row for the visible minority of Black, 3.5%. So we're going to have 0.035. Okay, so if I had to do this sort of manually, I would have to work out each probability individually. So this is going to be 1,000 choose 30 times 0.035 to the 30 times 1 minus 0.035 to the 1,000 minus 30. Okay, and then I'd have to do the same thing for 31. So very similar idea. Okay, and then I'd have to continue this for all of the different scenarios that fall into this category. So 32, 33, 34, 35, etc. Now, because we have Rcmdr available to us, we can simplify this a little bit. We know from Rcmdr that we can compute probability X is less than or equal to, do it like this, 39, which is equal to the probability X is less than 40, to be clear. And the probability that X is less than or equal to 30, or less than or equal to 29, which is equal to the probability X is less than 30. Okay, so in Rcmdr, we can compute these lower tail probabilities. So I can actually find the probability that I observe 39 or less persons that identify as being Black using the commands that we talked about earlier. Then what I can do is I can compute the probability that I observe 29 or less people that identify as Black and subtract that value from the first value. The remainder is going to be everything that sits between 29 and 39, which in this case is going to be 30, 31, 32, 33, up to 39. So the values that I want. So in Rcmdr, I can say distributions, discrete, binomial, binomial tail. I can say 1,000 is my number of trials. My probability of success is 0.035. And my first value of interest is 39. So this will give me the tail probability for X being less than or equal to 39. I click OK. I end up with the following, and that's what I have. Oh, sorry. I have the lower tail wrong. Lower tail. So I click that. I end up with the following, and that's what I have right here. Now what I need to do is I need to subtract off everything that's 29 or less because I want strictly between 30 and 39. So in Rcmdr, I use the same setup, except that I let the, the variable value be 29 now. Okay, I click OK. I end up with this, which is the value that I have here. Now I have the probability X is less than or equal to 39. I have the probability X is less than or equal to 29. And I can subtract X is less than or equal to 29 from being less than or equal to 39 to arrive at the answer that I'm interested in. Okay. Any questions? So we ended up with okay. So I think probably the trickiest part of this problem is just identifying what we're looking for and then making that lower tail subtraction. Because in this case, we actually set the lower tail to be equal to 29, so X equals 29, because we didn't want to exclude 30. We wanted to keep the 30 value, so we needed to subtract everything below that. So which is why we have 29 in the lower tail there. Okay. So let's look at another illustration here. More than 52, but less than 55 people identifying as Chinese. So we have X is equal to, in this case, 53, 54, 53 and 54, exactly, right? Okay, So we want more than 52, strictly more than 52, but less than 55. So strictly less than 55. So more than 52 is going to be 53 and above. Less than 55 is going to be 54 and below. The intersection of those is 53 and 54. So we're asking the probability x is equal to 53 and x is equal to 54. This is the same thing as the probability 53 less than or equal to x, less than or equal to 54, okay? And this is going to be the probability x less than or equal to 54 minus the probability x less than or equal to 52 in that case. Okay. Any questions on that? Okay, so in Rcmdr now, what are we going to need to do? We're going to go back. Well, sorry, we also need to identify n is equal to 1,000 again. P in this case, so we're identifying as Chinese in this illustration. So P is going to be 5.1%. So here we're going to have little p 0.051. Right. So we go back to Rcmdr, discrete, binomial, binomial tail. In this case, we're going to have 54, 0.051. Okay. And then we're going to subtract off being less than or equal to 52, distribution, discrete, binomial, binomial tail, 52, okay. Okay, so then here, we will have equals 0.6981531 minus 0.5933133. Which gives us equal to 0.1048418. So then in here, we can basically just say the same thing. So we have 53 less than or equal to x less than or equal to 54, which is equal to p x less than or equal to 54 minus p x less than or equal to 53, which is basically just following all the calculations I just did. Oh, sorry. That's more than 52, but less than 55. Identify as Chinese is equal to 10.484. Oh, yeah. All right. So we can continue on exploiting the calculator in various ways. So for example, here, at most 15 identify as Latin. So we have n equals 1,000 again. Oh, sorry. P in this case is going to be the probability that someone identifies as Latin. So going back to our table, Latin American, we have 1.3%. So that's going to be 0.013. We want X is at most 15, so less than or equal to 15. So X equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. Okay, so then the probability X equals is less than or equal to 15. Okay, so we can find this from Rcmdr. We're going to have distributions, discrete, binomial, binomial tail. So here we'll have 15, and then here we'll have 0, 1, 3. Click OK. In that case, we get 0.76472. So here we then have so it's going to be the same thing. At least 22 identify as Filipino. So in this question, we have little n is equal to 1,000. P is equal to, okay, so we're dealing with Filipino identification now. So that's going to be 2.3%. So here we'll have 0.023. Right. Okay, now at least 22. At least 22 means more than 22, right? So this is going to be X greater than or equal to 22, which means X equals to 22, 23, 24, 25, dot, 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 all the way up to 1,000 in that case. Okay, so we're asking the probability of being more than 22. So probability X is greater than or equal to 22. This is going to be the probability, this is going to be two things. One minus the probability that X is less than 21. Well, let's do it like this, is less than or equal to 22, which is equal to 1 minus probability X is less than or equal to 21. Okay, so in Rcmdr, we can use the lower tail. We compute the probability that X is less than or equal to 21, and we can subtract from 1. Or we can recognize that this is going to be the probability that, or the probability that X is greater than or equal to 22 is the same thing as the probability that X is greater than 21, strictly speaking. So then we could use the upper tail. So from Rcmdr, we have the following two options: distributions, discrete, binomial, binomial tail. So we can take 21, and this is going to be 0.23. Okay. Or we can do our upper tail calculation. And in that case, we can take strictly greater than 21. And then this gives us the following. Okay, so here we have 0.61246889. And here we have 1 minus 0.3875311, which is equal to 0.6124689. Okay, so they agree, obviously. Okay, so this is going to be following from here. Okay. Identify as Filipino is equal to 61.247. Any questions? All right. Okay, so similar idea here to the first problem. Okay, so in this case, we have no less than 5, but no more than 7 identify as Korean. So the probability that someone would identify as Korean, according to our table, is 0.5%. So it's quite low. So here we have equals 0.005. I think I'm missing a 0 there. Triple zero. No, double zero. Yeah, it's double zero. Okay. And then we want x is no less than 5. So greater than or equal to 5. And x is no more than 7, less than or equal to 7. Okay, so that gives us x equals 5, 6, 7 in that case. So we want the probability that 5 less than or equal to x, less than or equal to 7. All right, so in Rcmdr, we're going to use 2 commands. So this is going to be equal to the probability x less than or equal to 7 minus the probability x is less than 5. Which is equal to the probability x less than or equal to 7 minus the probability x less than or equal to 4 in this case. All right, so from Rcmdr, same idea. We're going to be using our probability of success counts of 4 and 7 in this case. So we'll have distribution, discrete, binomial, binomial tail, 7, 0.05. And then we'll do the same thing, but with 4. Oh, do I have upper tail on? I do. Sorry, one sec. All right. So then up here, we're going to have 0.8671524 minus 0.4400534. And that's going to give us equals 0.427099. So then in here, we would have for binomial 1000, comma 0.005. Okay. Probability 5 less than or equal to x less than or equal to 7 is equal to probability x less than or equal to 7 minus probability x less than or equal to 4. And then this is going to be what we had just worked out, 0.8671524 minus 0.4400534 equals 0.427099. And then we can say the probability that no less than 5 but no more than 7 identify as Korean is equal to 42.70710. Okay. So same idea again. So in this case, we want no more than 3. So this is going to be x less than or equal to 3, which is x equals 0, 1, 2, 3. So this is a nice one because we only have to do one calculation. So the probability that someone identifies as Japanese, according to our table, 0.3 in this case. So we're going to have p is 0.03. And we want the probability x less than or equal to 3. Okay, if we go to Rcmdr, we have distributions, discrete, binomial, binomial tail, and then we have 3, 0.03. Okay, that gives us the following. Right, so that was a nice, easy one. 1,000, 0.03. Okay, so the probability x less than or equal to 3 equals 0.64723221. The probability that we observe no more than 3, or sorry, the probability that no more than 3 identify as Japanese is 64.723%. Okay, and then here we have no less than 50 as Aboriginal. So we have n equals 1,000. X is no less than 50, so greater than or equal to 50. So this is going to be x equals 50, 51, 52, 53, all the way up to 1,000. So we want p x greater than or equal to 50, which is the same thing as p x greater than 49. Okay, so we can compute this directly from the table, or we can use the same trick we did before. This is going to be equals 1 minus the probability x is less than 50, which is equal to 1 minus the probability x less than or equal to 49. So from Rcmdr, we have two options. The probability that someone identifies as Aboriginal, according to the chart, is 4.9%. So that means that our probability of success here, is p equals 0.049. Right. So in Rcmdr, we're going to have distributions, discrete, binomial, binomial tail again. So if we use our lower tail, we're going to have 49, 0.049, which gives us this. If we use our upper tail, We have 49 again. Okay, so that gives us this. Okay, so in this case, we can just write directly that this is going to be 0.462094, or we can use our complement rule. We can do 1 minus 0.5379076, which is equal to 0.4620924. All right, and then here, to finish it all off, we have our little notation thing. So probability X is greater than or equal to 50 is equal to 0.4620924. The probability that no less than 50 identify as Aboriginal is equal to 46.209%. Okay, cool. So it took a bit longer than I thought, but that's a number of different examples showing how we can use the binomial tail probability function explicitly to find different probabilities that are of interest to us. You'll notice that in this illustration, we basically go through 3 different exercises. We have the illustration where we are between 2 values, so 53 less than x less than or equal to 54, for example. We have the probability we are strictly less. This is the easiest situation because this is just a lower tail calculation. And then we have the probability we are greater, which is technically an upper tail calculation, but you can also use the lower tail with the complement rule to find that probability. And I illustrated that both directions so that you have it. Okay, so there's another demo question that you can use, question 9, that's also a binomial probability exercise. So that will give you additional practice with the binomial probability formula. And in addition, as a reminder, on assignment 4, we have on question 4, this is a binomial probability problem. And the lab part is only asking you to verify A, B, and C. So basically, you can actually set this up already and get the answers to A, B, and C. And then you just need to show by hand that what you have from Rcmdr is the same. Okay, so is this going to be posted to YT? Yeah, I'll figure out a way. I'll figure out a way to get it to you. So that's, I'll stop the teaching part here. So I'm just going to turn off the recording. No, that's not it. I don't want to do that. And stop share. Here we go. Stop.